Hi friends, now let's get deeper into cryptography. Begin our journey with what we call classic cryptography. Before the ages of computers, or even ages ago, messages still needed protection. The messages earlier were being sent from one place to another place in a kingdom, from one king to another king, or such similar messages were being sent, and they needed protection from the enemies, and that is where the classic cryptography began. From Julius Caesar's to simple cipher where letters were rotated through the alphabet, to the mono-alphabetic substitution cipher where each letter had been a fixed secret replacement. Early ciphers were based on patterns and secrecy. Another powerful method was one-time pad, a theoretically unbreakable cipher where the key is as long as the message and used only once. But even these classic techniques had flaws. With enough ciphertext, clever attackers could spot patterns and break the code, and that's called cryptanalysis. Classic cryptography laid the foundation for modern encryption. Understanding it helps us see how far we have come from paper and pencil codes to today's unbreakable algorithms. So let's get deeper into what classic crypto is all about. It can be a simple substitution cipher where it's one of the oldest cipher systems dating back at least 2000 years, where whole kingdoms used to use this encryption technique, wherein the messages sent from one point to another point wanted to be safeguarded from the enemies. The enemies not to understand what messages are being transferred from one end to another end. They were using a simple substitution cipher method. The message here is encrypted by substituting the letter of the alphabet n places ahead of the current letter. For example, if n is 3, then the plain text A, B, C, D through Z was replaced by 3 places ahead, like A means D, B becomes E, C becomes F in the ciphertext. So in case of simple substitution cipher with n equal to 3, wherever we have A, we replace it with D. Wherever we have E, we replace it H. Wherever we have K, we replace it with N, and so on. And the plain message, say welcome to SKIT, here W will be replaced with Z, E will be replaced with H, L will be replaced with O, C will be replaced with F, and so on, and hence the cipher text will look like Z H O F R P H W R V N L W, and this is transmitted or sent from one point to another point, and before this communication began, the protocol was defined that the encryption is done using a simple substitution cipher method, where n is equal to 3, and other end we just transfer it back to the original text just by changing the encrypted text back to the plain text by just getting in a reverse way. So just Z, we look into the ciphertext and it represents W, and H represents E, then O represents L. So we just read back and we get back the plain text. So n equal to 3 was known as Caesar's cipher, and we have many way, so we can have any value of n, but n equal to 3 was used by Caesar's, and hence the name Caesar's cipher. So the decrypting is simple. So when you are trying to decrypt, we can if we know that encryption is done through simple substitution cipher, then we can try each of the 26 possible keys. So in place of A it can be B, in place of A it can be C, in place of A it can be D, and so on. So n equal to 1, n equal to 2, n equal to 3, we can try all possible combinations and can expect to find the true plain text and thereby recover the key with somewhere 13 tries on average. So that's brute force method. We can have an exhaustive key search, and because we are working with 26 characters in the English, so we can on average can try with 13 trials by checking the different values of n. So any permutation of 26 letters will serve as a key. That's another way. It's not necessary that I can just shift by value n. So you can just check any permutation of 26 letters. So that makes 26 factorial, that is 2 to the power 88 possible keys, and that makes too difficult to decipher what we have used. So assume that the computer is able to substitute at a rate of 2 to the power 40 keys per second. Even at this high speed of computation, we require somewhere around 9 million years to find the exact encryption key used for that. So it can be any permutation. So A can be Z, B can be P, C can be B, D can be D is one such example. Not necessary that what we have seen in the previous case where it is just shifted by some n, rotated by some n, so not required. It can be any combination, so it can be any permutation of 26 letters can be used to serve as a key. So that makes it is almost impossible manually to solve this problem, but anyway it is possible through system if we can make it, but still it looks too complicated to solve that. But intelligently, that is brute force we are trying to look at, but intelligently we can do find in a lesser time, and how that is done we look in our coming session. So please keep watching. If you find the session interesting, don't forget to hit the like button, share it with your friends, subscribe to the channel, and do comment whatever you want to say. So that's it for now. Keep watching. Thank you.